All right, kiddos, let's get started with vodcast 9.3. We're going to talk about ideal gases. I'm sorry it's a little stripped down this time. Obviously, we talked about this in class, and so the video is lagging behind what's going on in class. So if it seems a little rushed or stripped down, that may be a little part of it. And obviously, if you haven't watched the videos for 9.1 and 9.2, you need to go back and look at those as well. So to get this going, we're going to talk about ideal gases here. So it's kind of important to know what is the difference between an ideal gas and a real gas. So basically an ideal gas is something that always follows all of the points of kinetic theory. Now what does that really mean in practice? Okay, it means all these things that we talked about in kinetic theory back in the early part of the year. So it means elastic collisions for everything. Okay, it means no attraction or no repulsion between the particles. All of that stuff is part of what kinetic theory says about gas particles should be true. Okay, so an ideal gas is always following all of those points. The fact of the matter is that real gases don't do that. That at really high pressures and at really low temperatures, those things aren't true. Okay, so the particles do start to have attraction for each other. They are going to lose some energy in their collisions and all that stuff. So real gases then aren't quite the same as ideal gases. Now, obviously, we're talking about ideal gas law, so we're going to be doing calculations for ideal gases. But here's the thing. Most of the time, and certainly most of the time for like us in a standard high school lab, ideal and real are the same thing, because ideal gases and real gases, if you're at sort of a normal everyday temperature and pressure, like standard temperature pressure or room temperature and normal 1 atmosphere pressure, they're basically the same thing, okay? If you take AP Chem or some higher level Chem, we'll talk about how you can make real gases closer to ideal in calculations by adding in a few things, but we're really not going to worry too much about that at this level. So let's move on then to what the ideal gas law is. And what the ideal gas law is basically, we're going to take one formula and give ourselves a relationship between all the stuff that we've been talking about for a few days now. So pressure, volume, temperature, that's all the stuff that we did with the combined gas law in the last section. And then we're going to throw in something that's pretty important to us in chemistry, which is number of moles. Now, throwing a number of moles does a lot of stuff. I mean, it allows us to tie things into stoichiometry. It allows us to be specific about the gas, where that matters. It allows us to, talk about reactions and all that stuff. So the mole thing really matters. And that's what's going to really separate this equation from what we talked about yesterday in the combined gas law. PV equals nRT has pressure, volume, temperature, just like the combined gas law did. But it's also got number of moles. And the second thing that you should sort of notice is that there's no subscripts here. There's no like P1, V1, and T1 or T2 or any of that stuff. And that's because we're not talking about a change in conditions. We're talking about a static situation. There's something going on at this moment, and we're going to measure it under these conditions, and that's ideal gas law. Okay? So really the best way to do these is just to work out some of the problems. So let's talk about, first off, real quick, what all of the things are. So the R is one of the new things here, okay? And what R is what we call the ideal gas constant. When we say that something is constant, it means basically that it's the same number for us all the time. Now, there are actually different values for R, which would kind of make it not constant, but we're going to use the same constant all the time, and that constant has these units, okay? And it's kind of hard to see what the units look like that way because it's like a big, long, crazy thing all typed out. Basically, the units work out like this. It's liters times atmospheres over Kelvin times moles. Now, why is it like that? Because we are going to define then what the rest of our values have to be. Okay, so we'll get to that in just a second. So the other new thing is N. N is the number of moles. That's pretty simple. Moles are the units, so you plug in moles in that case. What that also enables us to do is that if we have something in grams or we need something in grams, we can calculate it for moles for a gas, and then we can use the molar mass to either convert it into grams, or we can take the grams and convert them into moles to plug into the equation using molar mass. Okay, so R and N, those are the two new things. The other things we had earlier this week. So we've got pressure, And here's one of the big changes right here. Okay, the pressure has to be in atmospheres. When we talked about combined gas law, we didn't really worry about that. We went ahead and left it in kilopascals and stuff like that. To use this R value that has atmospheres in it, our pressure has to be in atmospheres, otherwise it's not going to cancel out. Okay? Has to be in atmosphere. So what would you do then? Well, that goes back to what we talked about the other day where we did our conversions. So we got 101.3 kilopascals equals 1 atmosphere. Okay, all of that equals 760 torr. Okay, all that stuff that hopefully is relatively familiar. And I'll probably pop in since what I just wrote is basically illegible hieroglyphics. Okay, so you'd have to convert it if it's not in atmospheres in the problem. Next thing is volume. This also is going to be different, or your volume has to be in liters. Again, when we worked the combined gas law problems, we didn't really worry about that. If it was in milliliters or cubic centimeters or whatever, we just left it there. And then it kicked out the cubic centimeters or whatever, or they canceled out. But to make this cancel out properly, has to be in liters. Okay? And then the last one is temperature, and the temperature has to be in Kelvin. Now, the good news is that's not a change. Okay? That's what we did anyway in the combined gas law, but it has to be in Kelvin to make all this work out. Now, in the combined gas law that we did before, like I said, we didn't convert pressure and volume. You can convert them though. Okay, so like if you want to just put it in your brain that I'm always going to convert all my pressures to atmospheres, I'm always going to convert all my volumes to liters, and all my temperatures to Kelvin, that would be fine. It's not really necessary for the combined gas law. It kind of adds in an extra step, but like if it helps you to know it, then that works out fine. It's not, again, not absolutely necessary. And there may be some cases where you need kilopascals or something like that. But it might help you work out the calculations a little bit. So, best way to do these, just like with combined gas law, is to work some problems. So, example number 1. We got 3.5 moles of a gas in a 2.0 liter container at 20 degrees Celsius. What's the pressure? Okay, so right away, how do I know that I'm using combined gas law, or I'm using ideal gas law and not combined gas law? Well, you're like, well, we're doing the ideal gas law slide. Must be that, right? That's true, but the real thing is this. There are moles in the problem. We don't do moles in most of our combined gas law problems. Now, you take some college level chem classes, you'll see that you actually can do some mole stuff with the combined gas law, but it's not going to happen in any of the stuff that we're doing here. So what that means for us is that we already know one of our things. N is 3.5 moles. Okay? We know that volume is 2.0 liters. Okay, the good news is that's already in liters, so I don't have to do any conversion. Temperature is 20 degrees Celsius. Now, of course, we don't want it to be in Celsius. We want it to be in Kelvin. Okay, so we add 273. That gives us 293 Kelvin. Okay? And we're looking for pressure. So what equation are we using? We're using PV equals nRT, or as students often like to call it, PUV-NERT. Okay, that's basically what the equation is. And again, you won't have to memorize the equations. They're going to be given to you, but you need to know how to use them. And so we've got N, we've got T, we've got V, we're looking for P. The only thing we don't have here is R, and so remember that R is a constant, so it's 0.0821, or sometimes you'll see it 0.08206, which is, just another basically level of precision there, so nothing crazy there. And you got these crazy units. Now, here's what I recommend. If you are always converting into liters, Kelvin, and atmosphere, you don't really have to write the unit down. It's not going to hurt you. You probably should write it down. I think that's the best thing to do. But if you're sort of cramped for space or time, or you just find that confusing and it blows your mind, then don't write it. Just plug the number in. Okay? Because you know what unit you should get out with. If I'm doing ideal gas law and I'm solving for pressure, it has to come out to be atmospheres. Okay? It wouldn't work any other way. All right? So let's plug all these numbers in. So P times my V, which is 2.0 liters. That equals my moles. Okay? 3.5 moles. And really, if you're going to leave out the units of R, you can kind of leave out all the units. I try to write them out as best as I can because I think it's important. We've talked about dimensional analysis all year, and I would hate for you to sort of let that slide at this point. But if you're trying to make it as easy as possible, you don't technically have to write everything. But here's why they do have to be those certain values, because here's what happens right now. Kelvin is going to cancel. Moles are going to cancel. I've still got liters times atmospheres, but when we finish the algebra, liters are going to cancel also. Okay, so algebraically, how am I going to get pressure by itself? I'm going to divide both sides by 2.0. Okay, just a nice little step of algebra there. And so you plug all this into the calculator, and again, I know we talked about this some in class, but you can multiply all this stuff out first and then do the algebra, or you can just do it all in one fell swoop. Really kind of up to you. I have no real dog in that fight as far as the preference. You do what you're most comfortable with there. And we're going to get 42 atmospheres. Okay. How did I get to 42? I took 2 sig figs. Okay, I've got 2 here and 2 here. You might be looking at the temperature saying, isn't that technically 1 sig fig? It is, but temperature kind of works in squirrely ways sometimes with sig figs, so I kind of ignore that a lot of the time. If you're working on the test and you saw, or on the EOC and you saw an answer that was 42 and one that was 40, you probably want to pick the 40 because technically that'd be more right sig fig wise, but I wouldn't stress too hard about that. So let's work another one. This one's a little bit more complicated. So what's different about this one? It says grams of O2. Now, I don't have any grams anywhere in the formula. I mean, my formula is PV equals nRT, and the closest thing to grams that I have is N, and that's moles, but we've been doing stoichiometry and mole conversions for a long time. I can convert moles into grams, no problem, as long as I know what the chemical is, and I do. It's O2. Okay, so we'll get to that in a second. So basically what that means gas law-wise is that I'm solving for N. So what do I know? Volume, 0.745 liters. Temperature is 24 degrees Celsius, and I'm going to go ahead and add that in. That's going to be 297 Kelvin, just sort of converting that in my head. You can write that out, and that's perfectly fine. And then I've got a pressure that is 98.9 kilopascals. Now, we don't like that. Why don't we like that? Because we said that for ideal gas law, that it has to be in atmospheres, right? Okay, so let's do that. Let's turn that into atmospheres. I'm going to move it down a little bit so I don't interfere with the problem when we get to work it. But how do I turn kilopascals into atmospheres? This was the first thing that we did this chapter, was we converted temperature and pressure measurements. So 1 atmosphere on the top, 101.3 kilopascals. That's going to come out to be, let me see here on my sheet, 0.976 atmospheres. So that's my pressure. R is a constant. Always know what that is. Okay, and so we're going to plug that in. So in this case, I have pressure, I have volume, I have everything but N. N is what I'm solving for this time. So I'm just going to plug in all my numbers. 0.976 ATM, that's my pressure, times 0.745 liters is volume, equals N, which is what I want, times 0.0821 times my temperature of 297 Kelvin. Now, I think what works out best here is that you may want to do the math here and then do the math here and then do the algebra. I didn't do that. I did it all at once. So basically what I did was I took this 0.0821, man, that decimal point there is killing me. Okay, I took all of this and divided both sides by it. So that cancels that side out. And it leaves me like with one big honking piece of algebra over here, or math to plug in my calculator over here. But I kind of prefer that. You don't have to do that. You can break that up into little pieces. Probably best if you do. But the gist of that is that it comes down to be, I've still got N over here on the right, and I do all the math, and I come out with 0.0298 moles of O2. Now, I'm not done with the problem. In fact, I'm going to clear myself up some space here. Okay? Because that's not the end of the problem, right? The problem didn't ask me for moles. What did the problem ask for? Okay? Wants grams, right? So how do I turn moles into grams? Well, that's simple enough. We're going to take our number of moles, and we take the molar mass and turn it into grams. So 1 mole of O2. How do I know it's O2? Well, first off, oxygen's diatomic, but it says O2 in the problem. And so I'm going to multiply that by 32 grams of O2. And that is going to give me 0.954 grams of O2. Again, sig fig wise, I had 3 and 3. Had 2 here, so I mean, if you wanted to put 0.95 grams, I think that would be fully acceptable as well. Okay? So that's essentially how ideal gas law works. Okay? So that's the basics of it. Now, it can get a little bit more complicated. I'm going to show some stuff that you may or may not be responsible for depending on which of the classes you're in. Certainly everyone can watch it, but specifically the honors level class, you guys are going to have to work a couple of problems like this. So, 2 new equations, right? You're like, oh my gosh, that's crazy. Okay, well, these are just reformulations of the ideal gas law. Okay, it looks like it's really super complicated. It's not. It is the ideal gas law, PV equals nRT. Okay, just reformed to incorporate a couple of things. Okay, and so let me just real briefly run through this. We're not going to spend a ton of time on it because you might see 1 or 2 problems this way, but here's the way it works. Molar mass is capital M in this case. Okay, little m, okay, lowercase m, little m. Lowercase m in this case is the mass in grams. Okay, and by the way, big M, a molar mass is, as it usually is grams per mole. Okay, everything else is the same. R is the same, T is the temperature in Kelvin, V is volume in liters, P is pressure in atmospheres. Okay, and then the only other new thing here is the D. Okay, and that is density. Okay, and density in our case for gases is going to be in grams per liter. We did density earlier in the year, and it was grams per cubic centimeter. So I'm just going to work one quick problem here. Again, I wouldn't stress on this. I think we might have 1 or 2 problems that we're going to work on this, but we're not going to spend a whole ton of time on it. So find the molar mass of a gas with a mass of 6.82 grams. Now, let me give you a little hint. To be honest, you don't even have to do this special formulas, okay? You could plug this into PV equals nRT, okay? You could plug in your volume, your R, your T, your pressure, all of which is given to you, solve for N, that would give you moles. You would then take this grams, 6.82, and divide it by whatever your N was. That's all the whole formula is, okay? I'm going to work it out according to the formula that I gave you there, but you really don't have to. I know that some of you all took some of this homework home and I said, hey, we hadn't covered this problem yet. But I said you can figure it out with the ideal gas law, so you probably did already. And if you did, kudos to you. That's awesome. Okay, now if I look at my problem, I'm in Kelvin, I'm in atmospheres, I'm in liters. I don't really need to convert anything, so I'm just going to plug this stuff in. I'm looking for molar mass, capital M. Little m is mass, 6.82 grams. Okay, times R, it's our normal R, 0.0821. Okay, what are the units of that? Same as they've always been, liters, atmospheres, over Kelvin moles, right? Times the temperature, our temperature is 300 Kelvin. Okay, all of that over PV. P is 3.5 ATM. We're going to multiply that by 1.5 liters. Cancel out the units, liters, Kelvin, atmospheres. What am I left with? Grams over moles. Oh my gosh, grams over moles are the units of molar mass. So you just punch all that into the calculator. Okay, nothing terribly complicated there. And it's going to kick out 32 grams per mole. You know what the cool thing is? 32 grams per mole. Sounds kind of familiar, right? 32 grams per mole. So what's that gas? We can identify the gas from that. That means that that gas is most likely O2. It doesn't have to be. There's a couple other things it could be, but that's probably what it is. Okay? And then from there, you could easily take all of this stuff and plug back in for the density formula. I could take that 32 grams per mole, plug it in here, times the pressure, R and T, and I'd kick out a density. And if you happen to want to do that and punched all that out, you would get a density of 4.5 grams per liter. Okay? So, I mean, definitely a bunch of problems to work through, and hopefully you've worked all of the practice stuff. And if you haven't, make sure that you're going back, reviewing this, asking some questions, making sure that you're plugging everything in here. But that's essentially the gist of the math behind ideal gases. Thanks, guys.